Okay, section 7.2, we're going to now look at rational exponents. So this will move us really directly forward from what we were working on in 7.1. We looked at the radical, but we're going to see that a radical is really the same thing as a fractional exponent. That the two are the same thing, just different ways of writing it. You say tomato, I say tomato. Both are the same thing, I think. Okay, so what we're going to work with here is when we have an expression, some number to the 1 over n power, what they're just saying is, hey, it's the same thing as a radical. So in this case, when we said that, let's do this, square root of 9, that's the same thing as saying 9 to the 1/2 power, right? And since the square root of 9 is 3, 9 to the 1/2 power is also 3. You'll see this if you put it in your calculator. Just be sure when you do it in your calculator, because sometimes you go 9, you'll use the exponent key. Order of operations, if we do 1 divided by 2, it does exponents first, so we want to do parentheses 1 divided by 2. And you'll see that should give you the answer of 3. Okay. Cube roots, right? 27, remember that's 3 times 3 times 3. So if we have a cube root of 27, that is the same thing as 27 to the 1/3 power. And both of these end up being equal to 3. You'll see. Okay, so it's just a different way of writing it. The reason the radical was used for back in a long time ago is because initially when printing came up and such, doing these fractional exponents, because they're smaller, they just didn't have the print capability of doing that with movable type and stuff. It just really didn't work, so they found that using a radical for printing was much easier. Now we've got computers that can do anything. So, but in the bottom line is these two things are identical. So you'll see there's a lot of relationship between what we do in this section and what we did in the last section. So notice if a is less than 0, if a is negative, and n is even, just like we did last time, you don't get an answer. It's a non-real number. So since this is not a real number, right? This equals does not exist or undefined. If we were to take -9 to the 1/2 power, this also does not exist. So we'll see that. It's the same thing. Same thing. 49 to the 1/2. What's the square root of 49? 7. Right? There it is. The same thing as that. Exactly that. 26 to the 1/5 power. Let's see if we pull up our list here. 1/5, 26. Well, we don't have anything, but 26 is less. It's going to be less than 2. It's just going to be, plug it in. Yeah, just use the calculator. Okay, it kind of threw me off because it's not a perfect 5th degree thing. So it's less than 2. All right. And then 6x to the 1/2, well, that's just square root of 6x, and that's pretty much all we can say about it, okay? Because we don't know what x is. 6 is not a perfect square, so we're done. Now, the thing we can do, though, is that we maybe couldn't really work with when we had just the radical, is we can have something other than 1 in the top. So notice the index on the radical is the denominator, so n is the denominator of the fraction, but there also could be a power inside the radical, okay, either inside or outside, and that goes in the numerator. So this one or this one, same thing, really, because of order of operations, both will work. Then we get it in the numerator. Okay, so, and again, if a is less than 0 and n is even, then m to the n is not a real number. Of course, there's a caveat because you could square it first, but it's because if m itself is even, that would make this a positive, but it could also be on the outside. So we just say, hey, if a is negative number and you're using an even index, it's just not a real number. Okay, so we look at this. Now remember, it's this one, the denominator, is what goes on the index. So this is going to be -8 inside a cube root with a 2 either on the very outside or in here, however you want to do it. And you could do it either way. I think I might go like this. You'll see, I will see how they do it. So what's a cube root of 8? 2 times 2 times 2 is 8. So this gives us a -2. And then we can square that. That's going to give us a +4. This one is 10 to the 3/4. So what is that? That is, again, rewrite it as a 4th root of 10 raised to the 3rd power. And again, you could put the 3 in here or out here, either way you want to do it. I think that one's going to stop because you can't take the 4th root of 10. There's not anything that's multiplies by itself 4 times to get you 10. So this one, that's what they go with that route. They chose the same way we did. That's -2. -2 squared gives us 4. Okay. Here we get 10 to the 3/4. They put that in there, and you could do it that way. Then that way you can cube it, because 10 to the 3rd power is 1,000. Let's see, does 1,000 end up being something to the 4th root? No, that's 10,000. So we're done with it either way. That's the end. So, you could have, I kind of stuck right here, but they got stuck there. Okay. Same thing here, 81 to the 3/4 power. So again, remember, just rewrite it as a radical. It's going to be 81 to the 4th root, and then take it to the 3rd power. And again, we can look at our table and let's see if we've got something with the 4th root. Is there an 8? Oh, there it is, 81. So that 3, because 3 times 3 times 3 times 3 gives us 81. So there's going to be a 3, then 3 cubed. 3 cubed will get us back to 27. Take the 4th root of 81 and then cube it. So they kind of went a long roundabout the way we did that, and then they get to 27. Now on this one, we're going to do the sort of same thing, 14 to the 5th power, or you could take 14 to the 4th power first. Take the 5th root of 14 and then 4th it. Now the 5th root of 14, you could plug it in, cannot be evaluated by hand, right? So just put in a calculator. So this one, if you need to do it, just go ahead and put in 14 raised to the 4/5 power into a calculator, you'll get your answer. This is the correct way to do it. Notice the parentheses, because order of operations, this would take 8, square it, and then take that answer divided by 3. You get something else than what we were expecting than taking 8 raised to the parentheses 2/3. Okay, so this makes sure it's all up in the exponent. When you do it this way, the 3 is actually not in an exponent. It's a number that's dividing in. Okay. The other thing is negative exponents. What does a negative exponent mean? Well, it just means the opposite. Think of a negative as an opposite. And what does an exponent mean? It means to multiply, right? Repeated multiplication. So what's the opposite of repeated multiplication? Division. Opposite of multiplication is division. So when you have this negative, it can be rewritten as a positive exponent as long as you move it to the bottom. Okay. And again, with the exception that a is not equal to 0, because we still cannot divide by 0. Haven't figured out how to do that. Just doesn't happen. Okay. So here we got a negative exponent. So we can go ahead and rewrite this 1/81 to the 1/4 power. Take the 4th root of 81, and I think if we look at our chart here, 81, the 4th root, that's going to be 3. So that's simply going to be 1/3. So yeah, move it down. Take the fourth root of 81, that's 1/3. Now this one, the same thing, we're going to move the 64 down into the basement, and then 2/3, so we could take the third root, and again we come back to our table, a third root of 64, that's going to be 4. See how that works? Third root of 64, we know that's 4, and then we're going to square it. 4 squared is 16. Okay, but you'll see that I'll make sure I get this uploaded into Canvas. It's just real handy to look at this, and it makes it helps everything sort of come together. And a lot of times what they're assuming is that we just memorize this, and you just go, what kind of magic are they doing? How do they know? And they looked at the chart. Okay, a 7th root. So now let's make these into fractional. Now remember, the index is the fraction, is the denominator. So this just becomes, this is the numerator. So it's going to be 3/7. That's it. Remember, when there's no exponent or no index, that the index is actually 2. So, and then you could make it negative and move it up. We'll see if they do that. Here's a 5th root. So this is going to be this to the 2/5. And this one, since they're both inside there, it's going to be kind of a parentheses around here to the 1/4 power. So let's see how this all ends up working. Yeah, so 3/7, there we got it. They did move it up, and notice the 2 is the denominator, the 3 is the numerator. This one, the 2 is going to be the numerator, the 5 will be the denominator, 2/5. And here, 1/4 is going to be the denominator, and it'll be just a parentheses around this one. So you can't really distribute it over there. We'll see that that doesn't work. Okay. So rules of exponents. Let's go through this because it's helpful. So one rule is when we multiply exponents, and I'll use sort of the standard say x to the 4th times x to the 3rd. Okay, so what's happening here? What is x to the 4th? Well, that's x times x times x times x. X to the 4th, right? And x to the 3rd is x times x times x. And so when we multiply all these, remember these are just being multiplied. That's what an exponent means. What do we have? We have 7 x's all multiplied together. How could we get that? We could just add the exponents. So let's sort of think of exponents when we're dealing with them directly. So we're multiplying two things that have an exponent. Notice they have to have the same base. If they're different bases, this doesn't apply. But same bases, when we're multiplying, it becomes addition. I think of that as one step down, right? Because order of operations, we do addition before we do other way around. You do exponents, you do parentheses, exponents, multiplication, division, addition, subtraction. So they're at a different level. So when we're doing multiplication, what we do is we step down a level and just actually add the exponents. So this is 4 plus 3, which would be x to the 7th. See that? When we are dividing, say x to the 4th divided by x to the 3rd. This is x times x times x times x over x times x times x. And what we get is we get canceling going on. So this is a power. These all become 1. What's left is x to the 1 power. And notice we sort of just took 4, subtracted 3. So yeah, so we just subtract the exponents. Here's x. We do the top minus the bottom, and so that just gave us x to the 1 power. So that's division. How about a power to a power? So let's do this, x to the 4th raised to the 3rd power. Well, this 3rd power means we've got 3 of these, so that's x to the 4th times x to the 4th times x to the 4th. And we know from the previous rule, we could just add all these together, 4 plus 4 plus 4. That gives us 12. Well, 12, if we took 3 times 4, we would have got 12 anyway. So that's exactly when we've got an exponent to an exponent. Remember, take one step down from exponents. Where are you? Multiplication. So this is the one where we take 4 times 3, which would give us x to the 12th power. And those are your basic ones. What I want to show you, though, is what if we sort of did this one reversed. So we did x to the 3 in top with x to the 4th in the bottom. So if we look at this, 1, 2, 3 in the top, 1, 2, 3, 4 in the bottom, these all cancel out. That gives us 1 over x, right? But if we follow the subtraction rule, it would also give us x to the 3 minus 4, which is x to the minus 1. So that's that rule we looked at, is if you have a negative exponent, you just move it into the denominator. It works. It works from both perspectives. They've got a few other rules in here, but these are the basic ones, the basic really 3 with this rule here. The other rule they do is what happens if we have x to the 0. So let's do that because we can develop that here. Let's do x to the 3rd over x to the 3rd, right? Can you see that that's got to be 1 because something divided by self is 1? If we expand it, we get 1, 1, 1. So this has to equal 1. But we also know that if we subtract the exponents, that should give us the same thing. So this is x to the 3 minus 3, which is x to the 0. Anything to the 0 power equals 1. With one caveat, 0 to the 0 is called an indeterminate form. It's what Ramanujan is a famous, did I get the name right? I think he's a famous Indian mathematician, and he, as a young kid, he started asking his teachers why is that why is 0 to the 0 not something that's in that, and he drove his teachers crazy because he's just a smart kid. Okay, so those are our basic rules. We come here they are. If we're multiplying 2, what we do is we add the exponents. So the product rule for exponents, we add exponents. They jumped the gun on here. I would go with the quotient rule first, but okay, let's just follow their route. So something to the negative power, just move it down into the denominator. It works. Or if you've got a negative in the denominator, move it up to the numerator. This is really up in the numerator. Then it becomes positive. Another text I used called it the elevator rule. So put it on the elevator makes it positive. So think about kids. They love to go on elevators. Makes them happier. So if someone's in a bad mood, they're negative, put them on the elevator, make them happy. Same thing happens as this negative exponent when we've got a fraction. It works as making a reciprocal. Change the bottom to the top. Okay, so that's another sort of rule you could use. Here we got the subtraction rule, the quotient rule. So when you're subtracting two things with exponents, take the top minus the bottom. We did that one. An exponent to an exponent, just multiply the exponents and it works. If you have two things multiplied inside, this exponent is going to distribute. So exponents do distribute over multiplication. They don't distribute over addition, but only over multiplication. And they also distribute over division. So if you got a fraction in here, it kind of makes sense. You get both the top and the bottom to the same power. Okay, and then what we're going to do is we're going to work through a few exponents together. So this is a square root and a fourth root. So this is the same thing as saying this is x to the 1/2 times x to the 1/4, right? And since these have the same base, all we have to do is add the exponents. It's easy to say, right? So this is 1/2 plus 1/4. Do it this way. So we've got to get a common denominator. So 4 is going to be our common denominator. To get the common denominator, we do 2 times 2. So this becomes 2/4 plus 1/4. So when we add these together, we should get x to the 3/4. 1/2 and 1/4, kind of right what I wrote. This thing doesn't really erase, does it? It does. So now that I've talked about it, it's cool. I didn't know that. So let's erase it. Almost got it in the right place. 1/2 plus 1/4, that's what I set up there, is 3/4. Okay. Same thing's kind of going to happen over here. Let's change back out of the eraser. Let's go back to the pen. The pen is mightier than the eraser, right? So this is the 1/4, and then, but now we're multiplying, right? So this is going to be 3/4, because 3 times 1/4 is going to be 3/4. This, I believe, is one of our fourth roots. 256 is a perfect fourth root. And here we come to the fourth root. There's 256. That's going to be 4. See how that works? 256 is 4 to the 4th power. So we sort of distribute it here. This gives us 4 in the front and x to the 3/4 in the back. Okay, so it does simplify a little bit. Doing the same thing here. And remember, we can look this up. We're looking for a 5th root, 32 to the 5th. I believe that's going to be 2. So we have 32, yeah, to the 5th. That's 2. 2 times itself 5 times. And so we can distribute it. 1/5 here, 1/5 there. So this number just becomes 2. So it's 2x to the 1/5 and x to the 1/4. And then we're going to have some more work we can do, right? Because we're dividing by the x's, so we can subtract these exponents. 1/5 minus 1/4. 1/4 is actually bigger than 1/5. Yeah. So we're going to get a negative exponent. And again, the way they did this, they got common denominators. So 1/5 minus 1/4. 20 is going to be the common denominator. So we multiply this 4 times 4. 4, we multiply 5 times 5, or 5 over 5, right? Because this is a way of writing 1. So we've got 4/20. 4 times 5 is 20. Minus 5/20, which gives us 1/20, a negative 1/20. And then, I don't know, let's see if they make it, yeah, they push it back down to the denominator. There's sort of a lot of software likes to have positive exponents as your answer. There's nothing wrong with writing an answer with a negative exponent, but a lot of times they'll say, please write with a positive exponent. Yeah, they even said up here. I just don't always like to read the instructions. Assume that all variables are positive numbers. Well, actually, that's not what it says, the positive numbers. And we want to write our answer with positive exponents. Okay. So this one, remember this negative, what we can do is, I think they'll probably flip it first and make it positive. That's what I would do anyway, is yeah, just take the reciprocal, and that makes it a positive fraction. And now distribute the 1/3 to both of these. And it's cool, 3 times 1/3 is going to be 1. So that's x to the 1 power. And remember, 27 is one of our numbers that is a perfect cube, and the cube is 3. Okay. And we're getting close here. 4th root of a square root. This is getting messy. But remember, this is really just an exponent to an exponent. It is just, this is a 4th root. This is a half root. So we get this to the 1/2 raised to the 1/4. So we multiply 1/2 times 1/4. That'll give us 1/8. Okay. And then when we get to this one, what do? Well, we subtract exponents. You could actually flip it first. I think that's what I would do, is because you get negative exponents, it's hard to deal with. So I would flip it, make the exponents positive, then you can work with that. Oh, but they're different bases. This is what's cool about it. Different bases. We're done. So flip it, take the negative, move it to the top, the negative in the top, move it to the bottom, and we are done. Really done. So I appreciate you all sticking it out through all of this. keep making the progress. I'll try to make this as interesting, as fun as I can without getting too irreverent. But remember, I'm stuck inside all day too. I'm in my little room here making videos about math, and I miss seeing y'all. So, but we'll get through this together, right? And we'll be back. I'll come looking for y'all. We got email and stuff, so we'll keep in touch. We might be able to meet up after May, but we'll just keep seeing how things are. The main thing is that you're able to keep moving forward with your degrees and your plans and your progress. And I'm committed to doing my part to make that happen. So communicate with me whatever you need. If you need a little bit of time, you got it. We got 2 extra weeks. If you want to get done with this early, before that 2 weeks is up, you got it. We'll do it. So we're going to work with you. We're going to make this happen for you. And we're going to get successful so that you have a good, solid understanding. So when you take that next class, whatever that is, you're going to be well prepared. And remember, you can still get in touch with me. You've got my email. So we'll stay in touch. We'll make sure that you're going to keep moving forward and staying successful. Take care, be blessed, and bless others all around you. Thanks.